Okay, well, here we are for part 3. I paused part 2 to fix a mistake that I had made in the calculations here, and apparently pause and stop now mean the same thing. So let's pick up where we left off in part 2. The equilibrium constant is equal to x times 3x to the third over 1.20 squared. And when you run through all of the steps, you get that x is equal to 1.67 times 10 to the minus 2. So this is the correct version of that problem. And if that means that x is 0.0167, in other words, to write it in a simpler form. And that would mean that the nitrogen concentration at equilibrium, which is x, is 0.0167. The hydrogen concentration at equilibrium is 3 times that, or 0.0502. And the ammonia concentration at equilibrium is 1.20 minus 2x, which is 1.17 atmospheres. And those should be the correct equilibrium concentrations. If you want to check it, you can always put those numbers into the expression for the equilibrium constant. And if you put that number in, remember that the H2 concentration has to be up to the third power cubed. You end up with Kp of 1.54 times 10 to the minus 6. And that is very close to the 1.47 times 10 to the minus 6 they gave us before. And let's see. Next, we come to Le Chatelier's principle. And Le Chatelier's principle describes the effect by which it's almost as if equilibrium reactions are alive. That is, when they come to equilibrium, if you then disturb that equilibrium, they will kind of heal themselves. The reaction will shift either forward or backwards and it will do that, and it'll keep running in that direction until it reestablishes equilibrium. It's almost like one of those little Weeble toys for kids where you give it a push and it wobbles back and forth a few times, but then it eventually stands upright again. Well, equilibrium is kind of like that, and the guy named Le Chatelier was the first one to describe that scientifically. And this happens, basically this happens when a change in conditions that can affect the forward and reverse reaction occur. And what happens is that for a while, once the changes in conditions occur, the forward and reverse reactions will run at different rates. One of them will run forward and one of them will run backwards, and they'll run at different rates. And until they'll do that until the concentrations reach a value so that the ratio of products to reactants once again is equal to the equilibrium constant. And so the concentrations of products and reactants after the system is disturbed will be different from what they were before the system was disturbed, but the ratio of products to reactants will be the same as it was before. That's the important thing. And knowing Le Chatelier, basically knowing Le Chatelier's principle and looking at what changes are made and what the reaction actually is, you can predict which way the reaction will shift when a change is made. The formal statement for Le Chatelier's principle is if a stress is applied to a system at equilibrium, the reaction will shift in a direction that relieves the stress and reestablishes equilibrium. Stress in this case is defined as any change in conditions that will make it so that the concentrations present are no longer give the equilibrium constant when you take products over reactants. And some of these changes could include temperature changes. Temperature change actually changes the equilibrium constant. So that's definitely going to have an effect on the equilibrium. Changes in concentration, although they do not change the equilibrium constant value, they will force the reaction to run forward or backward for a while to reestablish equilibrium. So changes in concentration would include things like adding or removing a reactant or product. Also changes in pressure or changes in the volume of the container. But those only have an effect when there are gases involved in the reaction. There have to be some gases involved. The reactants and products don't all have to be gases, but there do have to be gases involved. Okay, the effects of concentration changes. If a substance is added to a reaction mixture, that's equivalent to increasing its concentration. And so what happens is that the reaction will shift in a direction away from the thing that you just added in order to reduce the excess concentration and reestablish equilibrium. So you add something, you've got too much of it, the reaction shifts the other way to get rid of it. So if more reactant is added, the equilibrium shifts towards products in order to reduce the added reactant. And if more product is added, the equilibrium will shift backwards towards reactants in order to use up the excess product. If a substance is removed, that's equivalent to decreasing its concentration, and the reaction will shift in a direction to replace it and reestablish equilibrium. If a reactant is removed, then the reaction shifts backwards in order to replace the missing reactant, and it ends up using up some of the product in the course of doing that. And if the product is removed, then the reaction shifts forward and runs in the forward direction for a while in order to replace the missing product. And in the course of doing that, it uses up some of the remaining reactants. There is a table on page 688 that summarizes these factors pretty well, so you might want to have a look at that. An example of questions like that might be the reaction between NaCl and Cl2 and NO. So you have two NaCl's in equilibrium with Cl2 and two NOs. And the question is actually asking us to find the relative values of Q and KEQ if the following changes are made, and also which way does the reaction shift. And those two factors are related to each other. I didn't mention the reaction quotient before, but the reaction quotient, of course, is concentration of the products over the concentration of the reactants using whatever concentrations you happen to have at the moment. And so if anything that increases products will increase Q. Anything that decreases products decreases Q. Anything that increases reactants decreases Q because reactants are in the denominator. Anything that decreases reactants will increase Q. So if we increase the chlorine concentration, chlorine is a product. If we have excess product, the reaction will shift backwards to use up the excess. And also, if you've added more product, that makes the numerator of Q bigger, and that makes Q bigger. So Q is now bigger than KEQ. Remember, you're starting with a situation that was originally at equilibrium, in which case Q was equal to KEQ. And now we're making changes to that system. And these changes we're making will change Q, but they won't change KEQ. And so whether Q goes up or down is kind of important. If you decrease nitrogen monoxide, NO, that means you've got a product that's essentially missing, and the reaction will shift toward that product to replace it. Okay. That also means that if you subtract from the numerator in the expression for Q, Q has now gone down. So Q is less than KEQ. And as we said in the last lecture, if Q is less than KEQ, then the reaction moves forward. If you remove NaCl, that is a reactant, and the reaction will shift backwards to replace the missing reactant, but also reducing the denominator of the expression for Q, reducing the denominator makes Q bigger. And so Q is now greater than KEQ, and that's a situation where the reaction would run backwards. There's also the effect of volume and pressure changes, but remember that that only has an effect when gases are involved. Okay, it's based on the fact that gases take up a lot of space relative to liquids and solids and aqueous solutions. And so increasing the volume of a container favors the direction with more moles of gas. If you have a bigger volume, it's easier for large amounts of gas to exist in a larger volume than it is in a smaller volume. But keep in mind, as you're comparing the moles of gas on the left side and the right side of the equation, that only moles of gas matter. Solids, liquids, aqueous solutions don't matter. Volume and pressure have no effect on them. It's only the gas moles that matter. Decreasing the volume is equivalent to increasing the pressure, and that favors the direction leading to fewer moles of gas. Makes sense that if you have less volume, then you can store less gas in that volume. Pressure has essentially the opposite effect of the volume. Increasing the pressure is like reducing the volume in that it favors direction leading to fewer moles of gas. Decreasing the pressure is equivalent to increasing the volume, and it favors the side of the reaction with more moles of gas. And the reason that pressure and volume are inversely proportional to each other is the ideal gas law. When you've got a sample of gas, the number of moles of gas is constant, if as long as it's the same gas sample. R, the gas constant, is constant because it's the same gas constant, or same gas sample. And temperature will be constant because we're not changing the temperature. So that leaves pressure and volume to vary relative to each other. And when you have something times something equals a constant value, then the two somethings are inversely proportional to each other. If you increase one, you decrease the other by the same factor. And so that's why the effect of increasing volume is the same as the effect of decreasing the pressure. And the effect of decreasing the volume is the same as increasing the pressure. Okay. So if you're looking at a reaction with gases in it, and you're wondering what effect a change in volume or pressure will have, what you want to do is add up the number of moles on the left side and the number of moles of gas, remember, on the left side, and compare it to the number of moles of gas on the right side. And that way you can tell which way the reaction is going to go. Now, in a lot of cases, like this reaction here, you'll come up with the same number of moles of gas on both sides. And in cases like that, a change in pressure or a change in volume will have no effect. Because remember, moles of gas act the same as each other in physical terms. It doesn't matter what the gases are. So in this reaction here, we have 1 mole of hydrogen and 1 mole of chlorine on the left-hand side. And we have 2 moles of hydrogen chloride gas on the right-hand side. That's 2 moles of gas total on each side. Changing the pressure or the volume in this situation will have no effect. No effect at all. And that's similar to having no moles of gas involved in the reaction because, well, if you have 0 moles of gas on the left and 0 moles of gas on the right, that is the same number of moles of gas on both sides. So yeah, that would be no effect. It's only if the moles of gas differ from one side to the other that changing the volume or the pressure will have an effect. There is a table on page 689 that summarizes this situation fairly well. And they explain it a little bit differently than I do. So it would be good to have a look at that because that might make more sense to you than what I just said. So it's always good to have multiple explanations. It's important also to remember that changing the pressure and the volume and the concentration of reactants and products will have no effect on the value of the equilibrium constant. Even if it's Kp, even if it's the equilibrium constant in terms of pressure, changing the pressure or volume will have no effect on the number. And that it will have an effect on the individual values. So the individual values for pressures or partial pressures of products and reactants will change, but the ratio of products to reactants will end up being the same as it was before. Okay. So we have this example here of a reaction that's inside a sealed flask. And we're going to make changes, and we're going to wonder, which way will the reaction shift? The reaction is nickel tetracarbonyl, which is what you call this thing, NiCO4 gas, is in equilibrium with solid nickel and 4 carbon monoxide moles. And the question is what kind of shift occurs for each of these changes below. So if you add some neon without changing the volume, what happens? Well, actually, adding neon has no effect at all because neon is not involved in the reaction. And it doesn't react with any of the things that are in the reaction by any other reaction. And so if you add something that doesn't react with any of the reactants or products, and it doesn't change the volume, then there's no effect, no shift. If you increase the volume, well, let's look at moles of gas. You've got 1 mole of gas on the left. It's a big molecule, but there's still only a 1 in front of it. So that's 1 mole of gas on the left. Now on the right, you have to be careful. Nickel is a solid, so that doesn't count as a gas. You've got 4 carbon monoxide moles of gas. And so you've got 1 mole of gas on the left and 4 moles of gas on the right. And so increasing the volume is equivalent to decreasing the pressure, which will favor the side with more moles of gas, which would be the right-hand side. So the reaction shifts to the right. And part C is asking what mass, if you increase the mass of nickel without increasing the volume or changing the volume, what will be the effect? Now you might be tempted here to say, well, nickel's a product, so if you increase the amount of it, the reaction is going to go backwards, away from the excess nickel. But the catch here is that nickel is a solid, and it does not appear in the equation for KEQ. For KEQ, it's products over reactants, yes, but nickel is a solid, so it doesn't, so it doesn't count. And so the KEQ expression is just carbon monoxide concentration to the 4th over the nickel tetracarbonyl concentration to the 2nd, or sorry, to the 1st. Yeah, I wrote the 1 in, it kind of looked like a 2 on the screen. That's a 1 there. And so nickel is not involved in the KEQ equation. And if something's not involved in the KEQ equation, then adding or subtracting it from the mixture has no effect. And so you can change the nickel all you want. As long as there's some in there, you'll get an equilibrium. Okay. Sorry. Well, that brings us to the end of what I wanted to do for today. We'll look at temperature changes next time. We'll definitely be back in person by Monday, but I still owe you a couple of videos for the days we missed last week, which I will be posting soon. And then just see if you can watch those before Monday. Okay, we'll see you then. Bye.